Hello and welcome to the webinar about unit testing and code coverage measurement with the unit testing tool Tessy. My name is Frank from the company Hitex, and I would like to start by giving you a very quick overview about the company Hitex, the company I work for. Hitex was founded in 1976 in Germany, so we are now 45 years old. Since 2003, Hitex is a 100% daughter company of the Infineon Group, the chip manufacturer. You can buy our products in every part of the world because we have a global setup with partners. What do? We provide, for instance, software tools, which means, for instance, compilers and also middleware like TCP/IP stacks or uh, uh, libraries for safety critical software. But the reason I'm speaking to you today is we are also responsible for sales, marketing, training, and the first level support for the unit test tool, Tessy. Hitex provides also unit testing services using Tessy and other tools, of course, not unit testing tools. We have products, for instance, Safety Pack, which is a library for safety critical applications. We provide services like engineering services, so you can develop products at Hitex. We have a production facility. We provide consulting, testing, training, and so on. And we are also preferred design house for the Aurix microcontrollers. The Aurix is a microcontroller from Infineon, and so we are expert in this area also. Okay, that's about Hitex, and now something organizational. During the webinar, you may ask questions using the webinar tool. I will not be able to answer these questions during the webinar live, but I promise that I do my very best to answer the questions in the next hours after the webinar by email. So feel free to, if you have any questions, to type them in the webinar tool. One question is superfluous. I answer it now. You will get the presentations which I used today and also access to a webinar recording. This will be sent out automatically later by email, probably within 24 hours. Okay, now we really start. Again, welcome to the webinar about unit testing with Tessy. I would like to give you a short overview of the topics I plan for today. First, we have to delve a little bit into the unit testing theory. What is a unit and what is the advantage and disadvantages? Then in the second point, we will see how code coverage and unit testing works in practice with using the tool Tessy. And because in this live presentation, we cannot cover all features of this unit testing tool, I would like to give you a very, very quick overview of additional features, of main features of Tessy in the end. Okay, so let's start. This unit testing theory part is in a different presentation. So now we're here. This presentation is also divided in two parts. First, we talk about unit testing of C and C++ programs in general, and then I need to explain how unit testing with Tessy works first in theory, because a lot of things are automated, and therefore you need to know what happens under the hood when Tessy performs unit testing. Okay, so first point, what does unit testing mean? I think this is the main question is what is a unit? What is a test object of unit testing? In my opinion, this depends on the programming language that you are using. And if you are using the C programming language, a unit or a module is a function in the sense of C. So unit testing means you pick up units, functions out of your application and test them in isolation. I say the test objects are sometimes called units or modules. This depends on the safety critical standards that you are using or the books that you have read. For instance, ISO 26262 calls the test objects units and talks about unit testing. IAC 61508, for instance, talks about modules and talks about module testing. And in my opinion, this is the same. If you have a C program, then the functions are the test objects. This is a little bit different if we have C++ as a programming language. Here, the methods of the classes are the test objects. And again, depending on the standard that you are using, you can call them units or modules. So, yeah. If we are clear about that, we can think of a software application as have an initial look like this. The red rectangles represent the units, can be functions in the sense of C or methods in C++. And the red arrows represent the calling hierarchy. And at the moment, the rectangles are in red, which means they are untested. And the question is now, what does unit testing mean for such a unit or such a rectangle? And to discuss this, I pick out a unit which has a calling unit above and calls itself another unit. So the question is now, what does unit testing mean for this unit here in the middle of this calling hierarchy? And this is explained on the next page. Unit testing means that you isolate the unit under test from the rest of the application, and then you test every unit by itself, one by one, and you test it rigorously. Rigorously means that you do not only use the normal input data, the expected input data, but also try to use, let's say, illegal value, unexpected value, and so on. Isolation is here represented by the blue line, which I call also the interface of the unit, and isolation is at 2 points. First, the isolation to the calling function at the top here. This is one, and the second thing is the isolation to called functions. In case our test object calls other functions, they are usually replaced by calls to so-called stub functions. This is the isolation to the called function. What are the advantages of this isolation? The advantage of the isolation to the calling function is that you can use arbitrary parameters. I'll give you an example for that. You see here two functions. The function f1 calls the function f2, and the function f2 checks if the parameter which is passed to it by f1, which is a pointer. So f2 checks if this parameter value is a null pointer. And if it is a null pointer, it returns a certain error number. And and you see here that the function f1 only calls f2 if f1 has checked that the parameter value, the pointer, is not a null pointer. This means during integration testing or during system testing, when where both functions are tested integrated, you will have a hard time if you try to check if f2 correctly checks for the null pointer and returns the correct error value. This is different with unit testing. In unit testing, you have the isolation to the calling function. This means you test f2 in isolation from f1, and then it is technically very easy to pass a null pointer to f2 and to see if f2 detects this correctly and returns the correct error number. This is the advantage of the isolation to the calling functions during unit testing. Okay, the second isolation point is to called function. I say again, if our test object calls other functions, they are usually replaced by so-called stub functions. That's for the linker, that the linker can resolve this call. Yeah, and this means unit testing is done in isolation, and everything outside besides the unit under test is under our control. That means unit tests are deterministic. That means if a certain unit test gives a certain result today, it should give the same result in a fortnight, because everything is under control and cannot change without our knowledge. That would be different if we use, for instance, called functions which are under development in our project. So that could result in different results of unit tests, but this is not the case if you use stub functions. This means unit tests are reproducible, and this is a prerequisite for regression testing. So it's very common that you can do regression testing with your unit tests, and regression testing is also required by a lot of safety critical standards, which means if you have, for instance, improved your test object a little bit by have a more clever algorithm or something like that, you can rerun the existing tests and they will give the same result if your refactoring was correct. Okay, again, this blue line here, which isolates our test object from the rest of the application, is called the interface of the function. And I would like to give you a more closer look on this interface. You see it here on this page here. The interface, you can say, has two parts, an upper part, which you probably are aware of. The interface consists of the input variables from the calling function to the test object, and also of the output variables which are passed from the test object back to the calling function, for instance, global variables. And of course, if our test object has a return value, the return value belongs to the output variables, or to the output of our test object. This is the upper part of the interface. And what might be astonishing is it also exists a lower part of this interface. In case our test object calls other functions, they are usually replaced by so-called stub functions. And in case our test object passes a parameter value to a stub function or a called function, then the value of this parameter is a result of the test case in question. And if you think that consider that the called function has, for instance, a return value, this return value is an input to our test object, and we hope that our test object evaluates the return value and reacts accordingly. So it's also an input. This means if you have a stub function, the interface is extended. Okay, that's about that. Now the hard part is gone. This shows you the situation after the process step unit testing. The rectangles are now displayed in green, which means each unit has passed its unit test, but the arrows are still in red. That means at this point, after unit testing and prior to integration testing, we do not know if the units interact correctly. This would be a task of integration testing, which we do not consider here in this webinar. Okay, this was a theory. Now, how is the theory applied for unit testing with Tessy? We know that the test objects that we consider are functions in the sense of C, or methods of C++. And the first step that Tessy does, it analyzes C source modules that you specify to Tessy, where your test objects are in. Tessy analyzes the C source module and lists all the possible test objects. And what is more important, Tessy also determines the interface of each test object. And we have learned about the interface of test objects here. That here is a more simplified version of it. as I said, the interface consists of the input variables and the output variables of the calling function. And the table here in the lower part of this page gives you an example of a very simple interface. The two lines which are shaded in gray represent a certain simple interface. This says, for instance, our interface consists of a variable a, which is input to the test object. We have also a variable named b, which is both input and output. Of course, a variable can be input and output at the same time. For instance, if you consider a global variable which is incremented by your test object, then the value of this variable is first an input value. It is read by the test object, and then it is incremented by the test object, and then it is written back by the test object. This means it can both be a variable can both be input and output. And here we have also a variable with the name c, which is only output. And in our example, the test object shall have a return value, and the return value is always output. So these two lines, which are shaded in gray, represent a very, very simple interface. Usually also the data types of the variables are included in the interface, but we have neglected it here. Okay, the interface determines the structure of a test case. This is an important sentence, so I repeat it. The interface determines the structure of a test case. This means if we have the interface, we know for which variables we have to provide values prior to the test, and for which variables we need to provide expected values. And this is here depicted in the third line of this table. Here's a line which is shaded in yellow. So we got a test case. If we say, for instance, okay, prior to the test, the variable a should have the value 5. And prior to the test, the variable b should have the value 4. And we expect that after the test, the value of the variable b is 8. So probably our test object doubles this value. And for the variable c, we expect that the value after the test is 17, and we expect that the return value of our test object is 42. That's how the interface determines the structure of a test case. Test case specification is a human task, in my opinion. So we need a human to think about the question, how many test cases do we need for our test object, and which values should the variable have. And this depends highly on the requirements for our test object, and also on the consideration of possible illegal values and extreme values and so on. So this is a more or less manual task, thinking about the test cases. But after that, with Tessy, everything is automated. The first thing that Tessy does, Tessy creates what we call a test application. This is depicted here. The heart of the test application, the main part of the test application, is our test object, which is here shaded in green. And the blue parts of the test application are generated automatically by Tessy. It's source code, see source code, and you see that it contains main. This means the test application is a standalone application. It contains also startup code in case you intend to run the unit tests on an actual microcontroller. You probably need startup code to get the microcontroller up and running, and this you can add this to the test application so that this works. And in case you have decided to replace called functions of the test object by stubs, Tessy generates the stub code automatically. So this is a complete standalone application. Test data is not included in the test application. This means the test application always has the same size, whether you have only one test case or if you have 1,000 test cases. This is important if you want to run the test application on small microcontrollers. Okay, the test application is generated as source code, and the next step is that Tessy compiles the test application to something executable. And there are different options. For the compilers that Tessy can use, you see here on the left-hand side, Tessy can use the native GCC or G++ compiler to compile the test application to something executable. If you do that, the test application will be a Windows application, and you can execute the test application under Windows. But usually you test embedded software, and yeah, it might not be compatible with a GCC compiler because you maybe use embedded keywords, special keywords which only your embedded cross compiler is aware of, and also there can be differences in integer sizes or in DNS or something like that. So you usually want that Tessy use your cross compiler to compile the test application in something executable, and this means you end up with a binary for a Cortex microcontroller, an Aurix microcontroller, or something like that. And then this raises a problem that you need an execution environment which is able to execute such a binary for a certain microcontroller. And with Tessy, this execution environment usually is a software debugger that you use in your embedded project. And Tessy does not really know if the software debugger acts as an instruction set simulator, and the tests are executed on the PC only and not on the actual hardware, or if the software debugger acts as a interface to, let's say, a JTAG debugger or an in-circuit emulator or something like that, and the tests are executed on the real microcontrollers, the real target hardware. What is different when you use GCC or an embedded cross compiler is the relevance of the test. I already mentioned GCC is a 32-bit integer micro compiler, so integers have a certain size. Your embedded cross compiler might be a 16-bit compiler for a 16-bit microcontroller, so the integer size might be different, so the endianness might be different. Other things could be different, like the packing of structures and so on. And therefore, the relevance of the test, which means how sure can I be that the results that a certain unit test provides in the end will also be the same result if I would execute this test on the actual target hardware. And it's clear that the relevance of the test is high if you use an embedded cross compiler with the options, optimizations options of your project and everything from your project, and then run the test on the actual target hardware, on the actual microcontroller. Therefore, the relevance would be very high. And if you do the same thing, the same test on on a PC with GCC, the relevance is rather low. I would like to compare two possibilities here, which are in these frames. This is a situation where a cross compiler is used, and Tessy uses the software debugger of your development environment to execute the tests. You see here in this picture on the left-hand side the situation where this debugger acts as instruction set simulator, and the complete tests are executed in the host environment without target hardware. And on the right-hand side, you see the situation where the debugger acts as an interface to a debug system. This could be a JTAG debugger, for instance, and then the tests are executed on the actual target hardware. And so the point here is that in both cases, Tessy communicates with the debugger, and Tessy is not really aware if the tests are executed on the target hardware or on the host environment. The only difference is if you intend to run the test application on an actual target hardware with RAM, you need to take care that, for instance, the memory layout of the test application fits to the memory layout of your target hardware. So if you compile the test application and you have stack at a memory area where the actual target hardware has no RAM, so the test will not run. So that's the only difference. So we have now the steps. Tessy creates a test application, compiles a test application, for instance, with an embedded cross compiler, and then executes loads the test application in the debugger, and then executes a test. And tests are executed in 4 steps. So first, the test input data is transferred to the test execution environment. In step 2, the actual test execution takes place. In step 3, the results are transferred back from the test execution environment to the PC. That could be transferred back from the RAM of the test application via JTAG, via software debugger to Tessy. And then in step 4, Tessy compares if the actual result is the same as the expected result. If yes, the test has passed. If no, the test has failed. And in case a test has failed, Tessy provides a very comfortable means to debug a failed test case. Of course, you can execute test cases alone. You do not need to execute all test cases in a row. So select the failed test case, and then Tessy is able to set a breakpoint at the beginning of the test object, and so you end up in your debugger, in your software debugger, at the beginning of the test object with the input data, which caused an unexpected result. And so we can you can do line steps in your test object, and you can debug why a test did not give the expected result. Okay, that's about the theory. Now I would like to show you the software tool Tessy. I do now close the camera, display the video, because to save space and bandwidth. What you see here is the user interface of Tessy. Those of you which are familiar with Eclipse will notice that it looks like Eclipse. Yes, that's true, because Tessy is based on the Eclipse-rich client platform. This means we have things like perspectives on the top. So we are here in the overview perspective, and we had a lot of other perspectives. Pools all the views which you have here in the lower parts of views, which the manufacturer seems sensible for a certain task. For instance, we have here a requirements management perspective, which allows to create requirements and link them to test cases. We will not use this perspective during this presentation. We have here the classification tree editor perspective, which allows you to create test case specification according to the classification tree method. But this is also not used during this webinar. We have a scenario editor for integration testing, because Tessy cannot only do unit testing, but also integration testing. What we will use is the interface perspective, which shows the interface of test objects, the test data editor perspective, which allows you to create test cases, and the coverage viewer, where we see coverage information. Okay, here in this, on the left-hand side, in the test project view, our test cases are created and organized in a tree-like structure. And because I already have some test cases, this view is not empty. If you do, for instance, an evaluation of Tessy, this view will be empty. And the first thing you do is to create what we call a new test collection, because the test cases here are organized in a tree-like structure, and the test collection is the root of this tree-like structure. You can have below an arbitrary folder structure. So I create just a folder for demonstration. I call it F1. And the leaves of this tree are called modules, Tessy modules, and I create now a module and I give it a name. And these modules here corresponds more or less to the C source modules or the C++ modules of your application under test. And I would now like to ask you a question, because we talk about the source modules, and the question is, which programming language do you prefer for the example I want to present you now? You can select between C or C++, so I'm open for both. Okay, most of you have voted, and I close the poll now because the result is rather clear. About 80% of you want C as the language of our example test object, and only 20%, 19%, yeah, prefer C++. So it's clear we have a test object in C. I hide it now, and I want to ask you another question. You can select which development environment I will use to demonstrate unit testing. We have the GCC, the native GCC, which will create a Windows application, and we can debug it with a CDT debugger of Eclipse, or you have the possibility to select a compiler from Kyle for, let's say, Cortex microcontroller, and then we will use Microvision from Kyle as a software debugger, as a test execution environment. And we have also the possibility to use an AR compiler for MSP430, for instance, and using CSpy from AR, which is included in the embedded workbench, as a debugger. And we can use another GCC compiler, but here a GCC compiler from Hitex, which is for the target Aurix, for the microcontroller from Infineon, and we would use the debugger UDE from the company PLS. Yeah, and I think the result, the decision is also rather clear. I close the poll now, and I would like to share it with you. And I think it's clear you voted for Kyle compiler from the MDK environment and Microvision as debugger. Okay, so let's see how I will do that. The first thing is I need to select the correct environment here in this menu, and please be aware I can here select what you have selected, so Kyle compiler, but please be aware I have made special arrangements to be able to select this compiler here, because I need to tell Tessy where this compiler is installed and which options for optimization shall be used and how it shall be linked and so on. So if you do an evaluation of Tessy, you only will be able to select the GCC compiler, the native GCC compiler, but not a cross compiler. But however, now I have directed Tessy to use this compiler. The next thing what I need to do is to select a source file for our example, and because you have selected C source file as test object in C, I select this is value in range.c source file, and I would like to give you a quick look into this file. I can use a built-in editor of Tessy, and I can see what it's inside. It's a very, very simple test object, a very, very simple file. There's only one function in this C source file. This means we have only one test object. This test object here is called isValue in range, and it solves a very simple problem. It answers the question if a value is inside the range, and the range is given by a start value and a length. And for instance, if we have a start value of 5 and a length of 2, so 4 is not inside the range. It's before the range, 5 the start value itself, it's inside the range, 6 would be inside the range, 7 should not be inside the range. From the specification, we have the specification here as comment. We see that the range is defined as a structure with 2 components, and we have also an enumeration type. The result can be yes and no, or no, which says, okay, of course, it's inside the range or it's outside the range. Okay, this is about the test object. Let's go back to the overview perspective. And if I click here, Tessy now analyzes this C-source module, which means it parses the C-source module. It lists all the possible test objects. We know already that we have only one test object available, and Tessy also determines the interface of these test objects. It takes longer as I expected, but now we have a result. This here is the name of the test object. We have only one test object. And if I go to the interface editor perspective, I can see the interface of our test object. And because we have a very simple test object, we have also a very simple interface. For instance, no external functions are involved, no other functions are available in this C-source file, no external variables are involved, and we also have no global variables. The only thing we have is 2 parameters. The first parameter here is a structure which represents a range. It has 2 components, the start value and the length. And the important thing here is that Tessy has determined that both components and therefore the structure as a whole has a passing direction in. In means Tessy has determined that the variables are only read by the test object and not written. And this is important for our test case because we need to specify values for these 2 variables for the components of the structure prior to the test. The same is true for the second parameter, which is the variable we want. This is a variable we want to know if it's inside the range or not. And Tessy has also determined that this variable is only read by the test object and not written, and therefore the passing direction is in, and therefore we need to specify a value for the variable we want prior to the test. The passing direction out is only here for the return value of our test object, and I told you several times, if we have a return value, it's automatically out. Passing direction is out, and we need to specify an expected result in each test case. We see here now also the data types and the values of the enum, but I think that's not interesting for the moment. Okay, that's the interface, and the next step is now that we specify test cases. We do this by in the test data editor. So I switch to the test data editor perspective, and here on the left hand side below in the test items view, I have the possibility to create a new test case in the context menu, for instance. And if I do so, I will get a column here in the right hand view, test data view, and in this column I can insert test data. And I have now created a test case, and I got a column, and you see the fields which are shaded in yellow are the fields where I need to insert test data, and you see also that the variables are organized, that the input values are on the top of the column and the output values are at the bottom of the column. So I start by inserting data, and I would like to use the values that I used earlier. I would like to make a test case where the start value is 5 and the length of the range should be 2, and I want to know if 6 is inside the range or not. And now I need to specify an expected result. And from the specification, I know that yes is the correct expected result for this test case. And because Tessy knows that the result is an enumeration type with only 2 possible values, Tessy can suggest that I can only select between yes and no, and I select yes, which is in my opinion the correct expected value for this test case. I can save this test case, then it is displayed in yellow, ready for execution, but prior to that I want to duplicate this test case. I can make a copy of this test case and I can paste it, then I get an identical second test case. I change the 6 to a 7, and from the specification, I know that 7 should not be inside the range. Therefore, I select no as expected result. And due to a programming error in my test object, the second test case will fail. I can now execute the 2 test cases just by clicking on this play button. The tests will not cannot be executed. The problem is that I need to start an execution environment prior for execution. So I will get an error message here probably. Don't worry about this error message. It's because microvision is not started. And I told you, if we use the Kyle compiler, we need to have an execution environment, and I do now start the Kyle compiler. And if I have started it, Tessy has an execution environment. It communicates with the with microvision and loads the test application, which was compiled with the Kyle compiler, loads the test application in microvision, and then executes the 2 tests. And because I do not have hardware attached, I use microvision as in instruction set mode. And now the 2 tests have passed. And as I predicted, the second test case failed, and this is due to a programming error in the test object. But prior to fixing this bug, I would just give you a quick look in the test report. I get a test report by just clicking on this button here, and you can have test reports as PDF or as HTML, as you see here, and also as Word, and always as XML. And you see here that we have some information about how the test application was created. Those of you which are familiar with the Kyle compiler see that we have a scatter file selected here and a startup code for an STM32. So actually it is compiled for an STM32 microcontroller. But what I want to show you is the result of the 2 test cases. You see here that we have a passed test case. The first test case has passed, and we see a failed test case. In the failed test case, the input values were 5, 2, and 7. So our second test case, the actual value was yes. We expected no. It was not equal, and therefore the test case failed. Okay, just to see how quickly you can create a test report. It was a simple test report because the test cases have no names and no specification and no description and so on. Okay, so next step now is to fix our test object, the bug in the test object, and to debug the second test case. And doing so, I can select only the second test case, and I would the important point is that I here have a tick mark defined breakpoint at test object, and if I execute the second test case with this tick mark activated, the test will not run to its end. We will stop in microvision, the debugger that we have selected for as test application execution environment, and then we can do debug steps to find out why we do not get our expected result. Again, the test application is simulated by microvision, but now we stop at the beginning of our test object and we can use the debugging features of our debugger. For instance, we can do line steps. And now we are at the first if instruction in line 41, and if I do another line step, I go to the second if instruction in line 44. And what I expect is that the next instruction is a return no, the same part of the second if instruction that would give me my expected result. But if I do another line step, I see this return no is not executed and the return yes in line 47 is executed, and this is my wrong result. And the reason of it, the culprit is a missing equal sign in the decision of the second if instruction. So, and yeah, if I have found out that, I can run the test application to its end. I have now an idea what I need to do to fix the problem, and I can use the built-in editor of Tessy to fix the bug. And the bug is a missing equal sign here in the second in the decision of the second if instruction, and I save it and I go back to the test data editor, and I'm now run both test cases at once, but I would like to ask you a question during this. I have the question, what do you think? Will test case 1 pass again? We have now made a fix to get test case 2 green. This probably will work, but the question is, will test case 1 still be green? And yeah, I do close now the poll. It is a difficult question, and I would share the results with you, and I can also show you the results of Tessy. Yes, the first test case has passed again. It is still green. So those of you who voted yes are right, but actually I would have preferred if most of you had answered one does not know, because in a general case we do not know if a test case which has passed will still pass after we have changed our test object. In this case we inserted an equal sign, and of course those of you who said it will not pass, yeah, are wrong. But yeah, okay, think about this question a little bit. I hide it again, and we are now in a situation where we have two passed test cases. Yes, test case 1 was not spoiled by the change in the source code, so we are lucky, but we did not really know in advance. Okay, you can say it was a very simple test object and I have seen it. Okay, what do we need to do now? If we develop a safety critical application, we are usually forced by our standards that we have to follow, that we measure code coverage. And the question is now, which code coverage have we reached by these two test cases? And this is quite easy to find out using Tessy. I just say execute and the two test cases, and I say measure coverage, and I have pre-selected to measure branch coverage and MC-DC coverage, and that's the two measures that are mostly used. I have here a table for you, which code coverage measures usually are used by standards or required by standards. We have here 61508, the general standard, and he mentions 4 coverage measures for unit testing: entry point coverage, statement coverage, branch coverage, and modified condition decision coverage. And the other 2 standards, ISO 26262 for automotive or 51228 for railway, both only mention statement coverage, branch coverage, and modified condition coverage. Tessy can measure all these 4 coverage measures, and also measures for integration testing, which are not depicted here. And you see that statement coverage, branch coverage, and MCD are the mostly used coverage measures in standards. Back to Tessy, I have selected to measure branch coverage and MCDC coverage, and now in this line here in the test project view, I see that C1 is displayed in the branch coverage is displayed in red. I have only 75% reached, and also MCDC, which I measured, is displayed in red. I also have only reached 75% MCDC coverage. And if you want to find out, where are instructions in our test objects that were not executed, or how this result was calculated, we can switch to the code coverage viewer perspective. And in this perspective, we see a flowchart of our test object with red and green branches, and of course red means not executed, green means executed. We see also the source code of our test object, which with red and green lines. Again, red means not executed, green means executed, and we can now select, for instance, a certain branch in the flowchart. You see here that the first one branch is displayed in red. It was not executed, and if I click on it, I see that it corresponds to the return no in line 27. This is a then branch of the first if instruction, which was not executed. If I click on this red diamond symbol here, I see on the right hand side that the decision of the first if instruction was always evaluated to 0 to false in both test cases, and we never had a test case where this evaluated to true, and therefore this branch was not covered. In the flowchart, we see here the assembled results of 2 test cases, entered, and in the second if instruction, 1 test case took the then branch and the other test case took the else branch. And if we want to know the path of, for instance, only 1 test case, I can mark the second test case here in this right-hand view, and now I see the path of the second test case through our code, and I see that the second test case took the then path of the second if instruction, the then branch of the second if instruction. I can also select green branches, and if I select this green branch here, I see that it corresponds to the return no in line 30. And if you recall, we just inserted the equal sign in the decision of the second if instruction to have this return no executed in the second test case. So everything is consistent, and this is also the end of the practical demonstration of Tessy. We have now one part to do a very quick look in the remaining 5 minutes on additional features in Tessy. Very quickly. The first thing is Tessy is certified by the TÜV for use in safety critical standards, and that it is appropriate for development or testing of safety critical application. The certificate covers for standards 61508, 26262, 51228, and 62304 from the medical area. And if the certificate is not sufficient for tool qualification in your project, a tool qualification package is available where you can qualify Tessy as a testing tool by yourself. I said Tessy does not only module or unit testing or whatever you call it. Tessy can also do integration testing. Integration testing is more or less that you assemble several units in a bigger, let's say, unit, which is called component here, and then you test it by a technical different mean. In Tessy, you can the component consists of several units, and you test if the units interact correctly during integration testing. I said that Tessy can also has a perspective for requirement management where you can create requirements, can link them to test cases, can then get reports which say, for this requirement, we do not have a test case or and we need another test case or something like that. And you should end up in a situation where all requirements have test cases and all test cases were executed and all test cases have passed. Tessy can also import and export requirements, usually in the requirements interchange format regIF. So, or if you want, you can also import in CSV files or text files and so on. This is a topic on its own which cannot be covered here in this short webinar. The next thing is, I already told you, Tessy can specify test cases according to the classification tree method. You see here such a test case specification. It consists of the classification tree in the upper part and on the test table in the lower part. A line in the test table represents a test case, and by the markers you see what each test case shall do. This classification tree method and the classification tree makes much use of equivalence partitioning. You see here, for instance, for this steering angle, we have 3 equivalence classes, left, center, and right. And so if you know from 26.26.2, there's a table which recommends to use equivalence partitioning for test case specifications. This is visually possible with the classification trace method here. Again, left, central, and right are equivalence classes. And 26.26.2 says also you should use boundary values, and you see here that, for instance, for the test relevant aspect speed, we have, for instance, an extreme value where one value is 0, or the maximum speed, and we also have invalid values like negative speeds or speeds which is a speed which is greater than the maximum speed. And so you see that this method also incorporates boundary values and illegal values and so on. Okay, again, this is very, very quickly and can not be covered in such a short webinar. Tessy can also display test data graphically. We see here, for instance, a representation of 20 test cases. The input is a beige step curve here, and obviously it should be smoothened by the test object, and the actual result is in green and the expected result is in blue. And you see that most of the time, for most of the test cases, actual and expected are identical and the test cases pass, but only for 3 test cases here we have a slight difference. And this is easier to spot in a graphical view than to look at Excel sheets and data and so on. Tessy has also a script editor perspective where textual representation of test cases are created automatically, or you can type it in. And the main point here is you can save such a script file in textual format, and you can put it under version control, and you can reload saved test cases at a later stage, and you can compare the progress of your test case specification. You have added test cases or changed test cases and so on. So Tessy can create a textual representation of test cases and can also import it, and you can type it in. You see here our test case that we used in the example. You see here start value is 5, 2, and 7, and 6, and so on. Tessy also features a command language, so you can write batch scripts which operate Tessy even without user interface. You can run Tessy in headless mode, and such a command language is requirement prerequisite for integration of Tessy in continuous integration systems. For instance, Jenkins, a lot of customers use Tessy together with Jenkins, and we have also videos and documentation how to integrate Tessy with Jenkins. Tessy is mainly a dynamic testing tool, but Tessy can also do a little bit of static analysis. Tessy can calculate some metrics, for instance, cyclomatic complexity and other metrics. And you see here that we can have a warning threshold and an error threshold, and depending on the values, for instance, the cyclomatic complexity is displayed in red or in yellow or in green. A very new feature of Tessy is that Tessy can automate mutation testing. This means Tessy, if you have a set of tests that pass, Tessy can automatically change the test object by, for instance, replacing a logical AND with a logical OR, and then rerun all the tests and find out if one of the tests fails, which means it has detected that it is not longer the original test object.